And then today we will have 6 talks by 6 invited speakers. The first speaker of this session is Professor Hamzi from California Institute of Technology. Would you share the screen? Yeah, thanks.
Do you see my screen?
Yes.
Okay.
The title of his talk is Kernel Flows and the Kernel Mode Decomposition for Learning Dynamical Systems from Data. Please.
Okay, thank you for the introduction and for the invitation, and thanks all for coming. So today I'm going to talk about 2 techniques that we have been working on recently in the last 4 or 5 years with different people that I'm listening here. And so they are mainly kernel flows and kernel mode decomposition for learning the dynamical systems from data. So the general context is how to analyze complex systems. And among the approaches to analyze complex systems are mainly the theory of dynamical systems and machine learning. So the theory of a dynamical system has been mainly developed by Poincaré and Lyapunov in the late 1800s. So it allows to analyze complex systems when the model is known, and it offers non-trivial ways to analyze dynamical systems. And it has the status of theory. So we don't need, if you have like a differential equation, for example, we don't need to solve the differential equation to now to have understand the qualitative behavior of the system. And but it's currently limited to low dimensional models and some very few high infinite dimensional systems. On the other side, machine learning is quite popular nowadays. So it is concerned with the algorithm designed to accomplish certain tasks whose performance improves with the input of more data. So it allows to analyze some very high dimensional complex systems when the model is not even known and based on data only. But among its current limitations, that is mostly a set of techniques and algorithms. There are no methodologies, and the theory is still underdeveloped. And it's not clear why the algorithms work and what is their domain of applicability. So looking at these 2 ways of analyzing complex systems, it makes sense to combine between them in order to strengthen each other. So we want to, in a way, we want to develop a new area at the interface of the theory of dynamical systems and machine learning as a field in the following directions. So machine learning for dynamical systems, and this is what this talk is about. So we want to analyze dynamical systems on the basis of data only, rather than attempt to study them analytically. And so this would allow to extend the boundaries of the classical theory of dynamical systems to systems where we cannot eventually write down the equations of the system, but where we have only data. So in a way, we want to revisit the main premise of the theory of dynamical systems, where we assume that we have a model and we want to say something about the dynamical system. Here we say we don't know the model, but we have data, but we still want to say things about the dynamical system. So in a way, we want to have a paradigm shift in a way in the theory of dynamical systems and revisiting the main premise and see what can be done. So one of the ways of doing it is, this is what this talk is about, is to try to approximate the vector field, the model. So we want to see if like machine learning techniques will allow us to have a good approximation of the equations of the model based on data. And the other approach, but is not covered in this talk, which is try to analyze directly the dynamical system, like studying stability properties or computing certain manifolds and this kind of things directly from data without having the equation of the model. And the other direction is the theory of dynamical systems for machine learning, where here we will see machine learning algorithms as dynamical systems. And we want to analyze algorithms of machine learning using tools from the theory of dynamical system. And so this will allow to give solid foundation to the existing method and understand their true potential and limits. So, and eventually identify the domain of applicability of the algorithm in machine learning. And yeah, so this interface, is quite important and relatively recent. It was pointed out, for example, about 15 years ago by Steve Smale in the introduction of the book in the footnote, that the unification of dynamical systems and learning theory is a major problem. And also developing a comparative study of useful algorithms currently available and giving them unity. And he meant like giving them unity within the context of the theory of dynamical systems is also an important point. And that's how I got involved in the field. So he encouraged both me and Jake Bouvry to work on this area during that period, 2007, 2010. And that's what we wrote, for example, in one of the papers where we said that it's easier to simulate a dynamical system and analyze the empirical data rather than attempt to study them analytically. But the mathematical theory was still under development. That's how I started the whole journey. So the goal of this approach is to combine, as I said, between the theories of dynamical systems and learning in view of a database, the qualitative theory of dynamical systems for analysis, prediction, and control. And the approach is to work in particular kind of Hilbert spaces called producing kernel Hilbert spaces and analyze the system in an RKHS where the analysis will be easier. And one possible link with the machine learning is the kernel trick. Someone talked yesterday about the kernel trick in the questions. Yeah, so in a way here we want to find nonlinear version of theories instead of just like nonlinear versions of algorithms using kernel methods. So the outline is to I'm going to talk a little bit about learning theory and kernel methods, and then also functional approximation and probability measures. And then I'll talk about the question of why it's important to choose the kernel, because we have many ways of choosing the kernel. And I will talk about parametric kernel flows, nonparametric kernel flows, irregular time series. This is what Zhong Chen talked about yesterday, so I'm just going to go quickly over it. Partial observations, and we talk about sparse kernel flows. And we'll apply this to different examples, including the climate modeling and a database of 132 chaotic dynamical systems. And then we talk about kernel mode decomposition, where we apply to the detection and possible prediction of critical transitions for some slow fast SDEs. And so, as I said, we assume that we are going to work in RKHS. So we have assumed that there is a mapping P from Rn into H that maps the variable little x into little z. And then we perform an analysis that is in general linear, but not necessarily linear. So in H, and then come back to Rn. So the whole story here is that we want to build a Hilbert space from data where computations and analysis in general would be simpler than working in the original space. So a kernel is a function of two variables, and it's the object that will allow us to define the map that takes us from Rn into H. So we'll be using this simple feature map, which is called canonical feature map or Aron-Dans feature map that we'll talk about in a bit. And so here, as I mentioned, so measurements or data are used to construct the Hilbert space where computations become simpler. So that's historically speaking, this method, including the Koopman theory, appeared in the 30s when people had complex problems, but they didn't have the computational power to solve this complex problem. So what they were doing is that they were looking for ways of simplifying the problem using different mathematical techniques. And speaking of Koopman, I usually get the question, what's the difference with Koopman and this approach? So So the people dealing with Kuffman are assuming that the model is linear in a higher dimensional space. So here we don't assume that the model is linear. So what we do is that we say that we embed the system into a higher dimensional system where the analysis becomes simpler, and the analysis can be linear, but not necessarily linear. So in a way, so we have the question of simplification, what it means to have a simpler way of doing an analysis. So the Kuffman people, they do it with assuming that the model is linear. But here we don't assume that the model is linear. What we assume is that we map the system in the RKHS where we apply either linear analysis, but not necessarily linear. So the key is just to simplify the analysis, and that's in a way similar in spirit to what people in quantum mechanics do. So they also have data, and then from certain physical systems, and they construct a Hilbert space from the data, and then they do computations in the Hilbert space, and then come with conclusions about the original system. So, what are these? They are, what are producing kernel spaces? As I mentioned, they appeared in the 30s, during that period of where people had to deal with complex systems. And then natural mathematical question was, when is it possible to embed a metric space into Hilbert space? That was a question that was asked by Schoenberg in the 30s. And then the answer is that if the metric satisfies certain conditions, it is possible to embed a metric space into a special kind of Hilbert spaces that are called reproducing kernel Hilbert spaces. And then they have been studied quite a lot in the 50s and the 60s, especially by Aaron John and Schwartz. And then research about them died a little bit. And then they were resurrected by essentially Wahba and her team in the 90s, and then Smail in the early 2000s and collaborators. So what are they? So we already saw people talking about this yesterday, so I'm just going to go quickly over it. Before anything else, they are Hilbert spaces with two extra properties. And the first one is the producing property, which is the property that is in item I. So which reminds us of properties of the Dirac function, that the evaluation functional that we have here is linear. And then we also have the closure of the span is dense in H. So in other words, an RKHS is a Hilbert space whose reproducing kernel is whose reproducing kernel has a span that is dense in H. Or in other words, RKHS is a Hilbert space of functions where all evaluation functions are bounded and linear. And so the important properties of reproducing kernels are that the RKHS is unique. So the kernel is unique, but the feature map is not unique. So there are many ways of constructing the feature map, as we're going to see in a moment. So we have property of symmetry, positive definiteness according to this definition. And we also have this interesting decomposition, which is exactly what people were looking for, is that so you want to write down kxy as an inner product in H. And Aaron John showed that actually an easy way of doing that is by just considering phi(cx) is equal to kx dot, and so kxy will be the inner product of phi(cx) with phi(cy). So that's exactly the question that was asked. So in a way, so k would play the role of the metric, and then you want to write this as to embed the metric space into Hilbert space. And so in other words, you want to write down the metric as an inner product in some different space. And so here we can talk about like a Mercer kernel that is that has the extra property of being continuous. So Mercer kernel is continuous and positive definite. And the fact that Mercer kernels are positive definite and symmetric reminds us of similar properties of Brownian and covariance matrices. And so this is an essential part of this work. Examples of kernels are the monomial and the Gaussian and the hyperbolic tangent. So one way, another way, here I talked about Aaron John's canonical feature map. Another way of constructing the feature map is by looking at the integral operator associated to a kernel that is given by LKF here. And then looking at the eigenvalues and the eigenfunctions. So since the kernel is positive definite and the eigenvalues are positive definite, so we can have the composition that we are looking for. So here a similar spirit. You see, we are separating the x and the x prime variable through this decomposition, sum of lambda j cj x cj x prime. And since lambda is positive, then you could write down this as the square root of lambda j cj x times lambda square root of lambda j cj x prime. And so this will give us Mercer's feature map, which is given by the square root of lambda I psi. So all you have to do in that case is to construct the integral operator, find eigenvalues and eigenfunctions, and then the square root of the eigenvalues times the eigenfunctions will give you the feature map. I mean, however, this theorem is not practical. Since P is not unique and depends on the measure mu, and it's also difficult to compute eigenvalues and eigenfunctions of this integral operator. However, it's an important. It's very useful in theory when one wants to have error estimates. So here I'm going to show how it's possible to compute feature maps without using Mercer feature map. So just by direct computation. In a way, this is like the third way of doing this. If we start, for example, just with the simple polynomial kernel in R2, so the inner product of x with t, so x is x, since we are in R2, it will be x1 t1 plus x2 t2 to the power 2. So you can expand it, so it will be x1 squared t1 squared plus 2x1 t1 x2 t2 plus t1 squared t2 squared. And this can be written as phi x times phi t, with phi x is this element in R3. So x1 squared, x2 squared, square root of 2x1 x2 times t1 squared, t2 squared, square root of 2 t1 t2. So you see here we got immediately phi by just direct computation. And similarly, one can do the same thing for the Gaussian kernel by just going from, in that case, from R little n to little L2. So RKHS play a role, important role in approximation theory, and this is how they have been used for a long time. So where the goal is to find an unknown function little f from random samples x, I, y, I varying from 1 to m. So here, a natural way of doing this is by minimizing this error criterion like little e, which is the integral of fx minus y squared 0. So this can be, the minimizer of this criterion can be found explicitly. F rho x is equal to the integral of y 0 y given x. But since rho is not known, then one usually what in practice what people do is that they discretize and approximate this error functional. And then this is approximated by the following criterion, which is the sum of fxi minus yi squared plus regularizer term that allows to have nice properties for the approximate. So then it has been shown that the solution of this optimization problem is sum of cj kxxj, and this kxxj is exactly the Aaron-Jones feature map. So as you see, it is linear in J, and the CJs are themselves solutions of this linear system of equations. So we have the linear properties of the approximation. Another application that we are going to need here as well, so which is the problem of change point detection. So we have we consider a sequence of samples x1 to xn from a domain X, and we are interested in detecting a possible change point tau, such that before tau the samples follow probability distribution P, and after the change point the samples follow probability distribution Q. So what we do here is that we map the data set into an RKHS, and then compute a measure of discrepancy delta n that is small if P is equal to Q, and large if P and Q are far apart. And so, yeah, a natural thing to do here is just to look at the difference between the means in the RKHS, and that's exactly what the maximum mean discrepancy is about. So this is like the metric that we'll be using as a measure of heterogeneity. And so basically what happens is that we map probability distribution P into RKHS and then compute its mean in the RKHS. And this is what is called the kernel mean embedding. So the kernel mean embedding is basically the mean of the probability distribution in the RKHS. And the maximum mean discrepancy between two probability measures P and Q is the difference between the kernel mean embeddings μkP and μkQ in H. And yeah, so here, luckily, one of the main advantages of kernel methods is that you don't need to work in the infinite dimensional Hilbert space. So you can do the computations in the ambient space, and then there is a way of computing the MMD in terms of kernels directly, and this is like an expression of the MMD in terms of the kernel. And one of its properties is that it is not a metric; it is a pseudo metric on distribution, so that it satisfies all the qualities of a metric except that the MMD of PQ is equal to 0 if and only if P is equal to Q. But luckily, this metric, the MMD becomes a metric for a particular kind of kernels that are called characteristic kernels. And these are the kernels that allow the map from capital P to capital H to be injected. But this is nicely satisfied by the Gaussian kernel, for example, both on compact and compact domains and on RD, for example. So this is just like an illustration of what I was talking about, is that you have probability distribution P, so you map it into the RKHS and compute the mean, so that's the mu KP. You have another distribution Q, you map it into H, compute its mean, that's mu KQ, and the MMD is the difference between the means. And that's just so this is like the other definition that I gave initially. So one of the nice things is that for characteristic kernel, the MMD metrizes the weak star topology on probability measures in the sense that the MMD between P and NP tends to 0 if and only if P and converges to P. So we have convergence in distribution if and only if we have convergence in MMD. And it is an integral probability metric that can be computed directly from data without having to estimate the density as an intermediate step. I mean, like classically, to find the metric between probability measures, one would need the expression of the probability measures. I mean, here we don't need to. All we have to do is to compute we can compute the metric directly from data, as we see from this expression. I mean, this is like an n by s estimate of the MMD. And this is the one that we are going to use in our work. So now we are going to look at the problem of learning chaotic dynamical systems. So here we are interested in learning the kernel. So the natural question here is, which kernel are we going to use for our problems? So we are going to use the method of kernel flows. So here, so the goal is to, so we are interested in approximating an unknown function from random samples, which is the problem that we talked about. So this problem, as we know, is ill-posed, but in the setting of optimal recovery, this problem becomes well-posed if one restricts candidates for the approximant to belong to a Banach space of function endowed with the following norm, and then considering the following the relative error. So this is leads to this method of kernel flows. So the premise here is that the kernel is good if there is no significant loss in accuracy in the prediction error if the number of data points is half. So that's the main. I mean here half is not to be taken literally. It's mostly compression argument. And so that, yeah, so kernel is good if so there's no significant loss of accuracy if we reduce the number of data points. And so this is what the relative error in that case becomes. So we'll have rho is the difference between the approximation of the function with the capital N points minus the approximation with capital N over 2. to the power 2 divided by the approximation, the norm of the approximation with capital N points. So that's exactly what this relative error is measuring. The difference between, in a way, it's measuring the compression performance of the kernel, and the kernel is good if it compresses well, in the sense that if the compression is well done and that we don't have a loss in accuracy, then the kernel will be good. So how do we? So if we have a parameterized kernel with by parameter theta, so the kernel flow algorithm can be described as follows. So first you have a large data set, and from it you take a sample of size capital N that we denote by x b y b from capital X capital Y, and from there we take a random sub sample. So here we do we take size capital N over 2. And then we compute the relative error that can be expressed as follows. So it's like 1 minus y transpose k theta minus 1 y divided by yf transpose k theta minus 1 yb. So this is like parameterized by theta, and that's a loss. So to find theta, one evolves theta in the gradient descent direction of rho. So in a way, I mean, this is like a trainable machine learning algorithm that is not no network. And the number of parameters here is just the number of parameters in the kernel. So we don't need to learn a lot of parameters like in neural networks. All we have to do is to learn the number of parameters that are present in the kernel. So let's look at the problem of learning chaotic dynamical systems. So here our goal is to forecast. We have a time series, x1, xk, etc. Our goal is to forecast xn plus 1 given the observation x1 to xn. So we work under the assumption that this time series can be approximated by a solution of the dynamical system of the following form. And our goal is to find f dagger and tau dagger. So here we are. Also, I'm not going to talk about how to find tau dagger, but you can find it in the papers. So I'm going to focus mostly on how to find f dagger. So here we are going to view this problem as simply the problem of learning an unknown function from random sample, which is exactly the problem that we were talking about initially in this presentation. So we have xk is going to be the past values of x, and yk is the future value. And we know that this problem admits a solution that is given by k little x capital X, k x minus 1 times y. And yeah, we are going to use different variants of kernel flows. So since we are dealing with dynamical system, we are going to use different variants to learn the parameters of the kernel. First version is the classical one that I just talked about, based on the relative error. The second one is based on the Lyapunov exponents. So basically, that we'll say that a kernel is good if the estimate of the maximal Lyapunov exponent obtained from the kernel approximation of dynamics that does not change much if half of the data is used. One can also use other Lyapunov exponents, I mean, not only the maximal one. Another one is to consider the metric associated to the MMD and minimize the MMD between two different samples of the time series. And the fourth one that I forgot to talk about here, but it's coming in the presentation, is it's based on attractor reconstruction. So remember here the goal, we want to learn, our goal is to learn dynamical system. So learning a dynamical system does not necessarily mean learning only the vector field. It also means that we want to have similar qualitative properties. And yeah, so essentially the first one is exactly about learning the vector field, but the other ones, I mean, this one is about like learning Lyapunov exponents and then deducing the vector field. So that's what this metric is about. So making sure that the Lyapunov exponents of the true system versus the approximation are close enough to each other. Third one has like more of statistical properties, in the sense that we are saying that we want the MMD, that the statistical the statistical properties of the true system versus the approximation to be close to each other. And the fourth one that I did not write here is that we'll say that kernel is good if the Hausdorff distance between the true attractor versus the reconstruction of the attractor from data are close to each other. So here our goal is also long term in the similar way of the Lyapunov exponents, but in view of attractor reconstruction. So that's these are like 4 variants of kernel flows that we are going to use in our case. So let's start with like some prototypical chaotic dynamical systems. So we use this simple kernel for some examples here, like the Bernoulli map and the Lorentz. And so you see the number of parameters here is quite small. So we don't, I mean, like if you were to use like a neural network, and then we'll have like an issue of finding the number of layers, the number of neurons per layer, and so the number of parameters, which are the weights, are going to be bigger. Here we are going to use mostly a few parameters. So that's the example of the Bernoulli map, which is like prototypical chaotic dynamical system. So here we see the importance of choosing the kernel. So you see the second picture is what happens for this kernel if we are using like random parameters. But after learning, you see the first figure allows to show that we have a good good performance when it comes to prediction. Same here, like third figure is for different initial conditions. So blue is true, red is after learning the kernel, and then green is before learning the kernel. Then we move to the Lorentz system. So here, so we do similar way of thinking. So this is after learning the kernel. So these are the time series of X, Y, Z, and these are the errors. So the errors. So red is after learning the kernel, and then green is before learning the kernel. So we see there is a substantial change in the approximation, approximation errors, and that's the projection of the attractor on the X, Y, X, Z, and Y, Z axis. So first, third, and fifth figure are after learning the kernel, and second, fourth, and sixth are before learning the kernel. And this is what happened in the third in 3D for the attractor. So then we apply this to a problem of climate modeling. So we have so we apply this with this joint work with Omid Malik and Houman Wahadi. And so here we applied this to some data set that they use at Argonne National Lab. So here we have method of kernel flows is the blue, HiCom is the orange, and green is the CSM. So these are PDE method, and true is the red. And see the performance is quite good. And here I just use my own personal laptop. And so there is also LSTM. So here you see the training using the different PDE method. So here is 800 core hours on this supercomputer, 17 million core hours on this supercomputer, 3 hours of world time on another supercomputer for LSTM, and 40 seconds for Kernel Flows. So this is quite interesting. And the same thing, it applies not only to short term, but also we see for long term. Same thing, we have the comparative profile, satellite profile. So these are true, Kernel Flows, HiCom, and CSEM. So these are like good performance compared to this PDE method. Another way of learning the kernel is by doing kernel warping. So we, instead of learning the parameters, what we do is that we modify we do kernel warping. So we modify the variable. So so we have kxx prime phi. So this is like the modification of the kernel, and we modify x and x prime through phi, and phi is done through a dynamical system. And this dynamical system is given by the following ODE. So we start with our data x1 to xn, which are the initial condition, and then we do modification, we do warping of the data, and so this will give us the phi, and then the phi is going to define the new kernel. And this is done usually by just in practice we just use the Euler discretization, but one can use other discretization schemes. For example, this is what happens to Bernoulli map. So here we have you see the true versus approximation with the relative error, which is the first version of Kernel Flows, versus rho MMD, which is another version of Kernel Flows. And so this is the warping that I was talking about. For example, you start with blue is true, so phi LXN is equal to XN. But then after the warping, this is what the green after 500,000 iterations, and that's what happens to the dynamics. The before is this green to xn plus 1 is equal to 2 mod x1 xn. These two lines, and then after being deformed, this is what they become. So we have this tails in a way. And this is the dynamics of the rho function. So this is for the loss of the relative error, and then this is the MMD. So that's what we have. So this is the part that Zhong Chen talked about for a Kernel approach for learning irregularly sampled time series. So I'm just going to go quickly over it. So here, as he mentioned, I mean, the trick is that we are going to work in an extended state space. So instead of using xk plus 1, etc., we'll be working in the extended space of xk delta k. So this is what the trick here is here. So in a way, so it becomes like more time-aware time series representation of the dynamics. So that's what he talked about yesterday, so I'm just going to skip it. So now we are going to talk about partially observed dynamical systems, where we have a dynamical system where we assume that some of the variables are not known and other variables are known. So we are going to, in a way, we are trying to recover Kalman filtering for Kernel Flows. So we only observe xn, which is the first m components, and then we assume that the other one, the m1s, the remaining m1s are not observed, and our goal is to forecast xl plus 1 given the observation xn1 to xn. So this is what we are going to work with I didn't talk about it here, but essentially it's about computational graph completion that Yasamin talked about yesterday, and as well as Human actually. So we are going to modify the criterion that we are going to use, and then we are going to get like different way of approximating the function. So basically, we'll be having a representative theorem with some variables that are missing, but that will be a solution of this following optimization problem. And so that's what we see here, for example. So here we did it for Lorentz case. So first we consider, so we did like two cases. First, we have access to x and y, but not z, and then we did have access to x only, but not y and z. So here we had the base kernel had to be increase a little bit. So first we are going to find the auxiliary variable in a way which is like the variable that we are going to use in the representative theorem, and then use the following kernel, and then apply Kernel Flows to learn the parameter of the kernel. So that's, and then what we notice as well is that we'll have to also increase the time delay that we are using for approximation. So it makes sense because we are missing information, so it makes sense to go further in the past. And so that's what we have for x and y and z, like true versus approximation. And these are the errors between true and the approximation. And that's what happens to the reconstruction of the attractor. So true versus approximate. And now, I mean, more recently, we talked about introduced this version of kernel flows called sparse kernel flows. So one of the limits in the parametric versus and the non-parametric kernel flows that I talked about now is the base kernel. It's the kernel that you start with. I mean, how do you choose it? So it was mostly done by hand, for example. For example, this one. I mean, how do we choose the first? How do we choose the first one to learn its parameters? So that was one of the things. So what we end up developing now, so instead of doing a bottom to top approach when it comes to kernel learning, so we are going to adopt another approach, which is like top to bottom, in the sense that we start with a large dictionary of kernels that is the sum of little m baby kernels in a way, and we do sparsification. So we are going to do optimization with this lasso term, so the lambda norm L1 norm of theta, and then our goal is to zero the maximum number of terms in this large kernel. And we apply it to a database of 131 chaotic dynamical systems. That is like one of the papers that I think it was introduced by Gilpin. So William Gilpin in about 2 years ago. It's like a nice database like for checking algorithms. So what we did is that we use this kernel that has like 15 terms and about 40 parameters, and we applied it to this 132 chaotic dynamical systems, and then the method worked quite well. So for example, one of the examples here is this 3D chaotic dynamical system, and so that's, for example, the regular kernel flows where lambda is equal to 0. So that's the true versus approximation of the attractor, and this is with sparsification, so the true versus approximation, and that's same for another chaotic system, a true system. So that's the regular kernel flows lambda is equal to 0, and sparse kernel flows with lambda is equal to 2. And yeah, so that's regular kernel flows, and these are the errors. Like short term, like SMAP is versus sparse kernel flows from 6 10 to the power minus 3 to 3 10 to the power minus 5. And the Hausdorff distance, when we see that it's being reduced, like the true regular kernel flows versus sparse, regular kernel flows versus sparse. So that's about kernel flows. And then lastly, I'm going to talk about detection of critical conditions for some multi-scale SDEs. So we are going to focus on this slow pass SDE. So we and that have critical transitions. For example, we start with the van der Pol model, stochastic van der Pol with noise. So this one has a limit cycle, and we can show that, for example, that by looking at the MMD, that it is maximal at this critical transition. So we can prove analytically that the MMD. So what we are going to do here is that we are going to take a sliding window, and then we divide the sliding window into 2 parts, and then compute the MMD between the first part and the second part, and we show that the MMD is maximal at this critical points. So that's one way of detecting critical transitions. The other way, I mean, we are going to use kernel mode decomposition, which is a way of constructing kernels in order to detect patterns. So here, the pattern that we are interested in detecting is the critical transition. And so what we did is that we extended kernel mode decomposition to detecting patterns. And so here, this is what in a way, it's like a Gabor wavelet inspired kernel. So instead of using the cos, we use the y, which is like the pattern we are interested in. And then from there, one constructs the gram matrix K which is like CSCT, which is this function here. And this will be a micro-local kernel, and then we integrate to get the full producing kernel. So basically, yeah, K, that is inside the integral. The integrand is to detect the patterns, and we have a simple expression, and then you integrate with respect to all the different parameters, and you get the kernel. And for example, for stochastic van der Pol, I mean, that's the pattern we are interested in. I mean, that allows us to construct the baby kernel. And you see, like the old kernel, without considering which is like a Gabor inspired, Gabor wavelet inspired is red, but then the new kernel encodes the critical transition within it. So it's in a way it also becomes discontinuous at the critical transition. And so that's the reconstruction of the signal and the noise in the system. So by noise here we mean intrinsic versus the extrinsic noise. And then we also talk about we wanted to see if it's possible to extract an early warning signal. And so this is how we define the energy of the sliding window as the following. So this one is a quantity that you can compute through the kernel, and then in given sliding window you compute this energy of the sliding window, and we could see that there is a possible way of constructing early warning signal. So if yeah, for a very small value of tau that shows up in this energy, I mean the only one, the energy and the signal, they match. You see that there is like an exact matching. But then by playing a little bit on this parameter, you see that we could see that it's increasing just before the critical transition. And this is what we are going to define as, so in a way, as good early warning signal. So for some values of tau, if it's very small, then it matches exactly. Then if it's like relatively small, then you could extract an early warning signal, but it cannot be too large, because otherwise it will miss the critical transition and then will end up containing many critical transitions. So it's good to, so there is a way here of, yeah, this is what I was saying here, that you could eventually extract an early warning signal here. I mean, it requires more work, but giving this numerical experiments, we could see that for certain parameters of this kernel, we can fine tune, and then you can eventually detect and predict critical transitions. And yeah, so I'm going to stop here. So basically what we did here in this talk is that we used different variants of Kernel Flows to approximate chaotic dynamical systems, and including the climate models as well as 132 chaotic dynamical systems with a relatively simple kernel, like a maximum 15 terms and 40 parameters in total. And we used also the maximum indiscrepancy and extended kernel mode decomposition to detect critical transitions for some SDEs. And I forgot actually that we applied it also to a problem of seizure detection, and then the results are promising. It's still like work in progress, but for some models that we had, so including a model of the slow fast SDE for critical transitions, which is a 9-dimensional model that I did not talk about here. So you can find it in the paper. And so yeah, these are list of references that you can find on arXiv and ResearchGate. Yeah, thank you for your attention, and I'm happy to take questions.
Thank you very much. Thank you very much for the nice talk. Yes, so Lyudmila, yeah, you can start the question.
Can you hear me?
Yeah,
Yes.
I can hear you. Hi, Lyudmila. Hi.
Okay, hi, Meridian. Thanks a lot for the talk. So I have two questions. One may be a short one, and another one more to the essence of what you are doing. So the first one has to do with this MMD. So I've been trying to work with this MMD in the context of dynamical systems. So what exactly are those S1 and S2 that you are measuring your MMD on? So are these realizations of time series? What is that exactly? So that's my first question. And the second one has to do with this combination of kernels that you are taking. So if one works with a kernel that can be characterized as universal, so what is the idea behind, let's say, working with a linear combination or putting together these various kernels that you have in different instances on your slides? So what is the idea behind why you would want to do that?
Yeah, okay.
So these are the two that I have.
Yeah, okay, yeah. So so for the first one, for the MMD, so there are so the here S1 and S2 are two different. I mean, there are actually two ways of computing S1 and S2. So one of them I tried both, and they both work in the examples I had. So one of them are you have a time series and you take two different samples. S1 is one random sample, and the second one is another random sample of one time series. So you have like one initial condition, and then you take first random sample, for example, from T1 to T2, and the other one is from T2 to T2 to T3. It's two different intervals, and then you take two random samples from two different intervals. The other version I use is just take one interval, take one random sample, and then another random sub-sample from the first one. So you take, for example, capital N points in the interval T1, T2, and then from within the capital N points, you take capital N over 2 points. So here that's the two versions.
But maybe my question is more about what exactly that measures, right? So
what measures? Yeah, okay, okay, yes. I thought you said how to compute. Yeah. So what it's measuring, I guess. So if you look at this expression of the MMD that is here, you see it's measuring correlation, but in a more sophisticated way, right? So if you take, for example, the Gaussian kernel, well, okay, let's start with the linear kernel. If you are starting with linear kernel, you are just computing the difference between the means. But if you are doing Gaussian kernel, then you are computing all the covariance, all the moments, the difference between all the moments in between different samples of the time series. So you can difference between means and then variances, and then all the moments up to order m. So that's what the advantage of using this is, that by just looking at so you are basically looking at the difference between the statistical distribution. Yeah, but like deeply within, maybe this is what you are asking about. It's mostly the way I see it is that we are looking at the Frobenius-Perron operator. So in a way, we have probability distribution on the initial conditions, and then you want to see how it's evolving with time through the dynamics. But I don't have a proof for this. I guess that intuitively this is what's happening. That in a way we are looking at the statistical properties of the dynamics through the Frobenius-Perron, but I just have no proof. But intuitively, this is my guess. Maybe this is the essence of your question, isn't it? Yeah. And then the second question is about so where these kernels are coming from, or what was the question?
Why you are combining them in this way, in this particular way, right? So if you're working with universal kernels, so why one wants to work with their linear or non-linear?
So linear combination was just the easiest way of doing it. I mean, there are probably other ways. I mean, I think that maybe also product, or why not multiplying, right?
The question is more like, why wouldn't you just use one family of universal kernels and you use just the kernel, right? Why are you combining them in this particular way?
Yeah. Actually, this is how I started, and it didn't work. So, for me, I thought when I started doing with looking at the Bernoulli map and the Lorentz, so I thought, okay, I'll just start with the Gaussian kernel and it would work. But then it didn't work. I mean, that was the issue. That's one simple universal kernel, like Gaussian, didn't work. If you change the initial condition, the performance were not good, and if you apply it to a climate model, it just didn't work. So the idea was that that I look at all the possible prototypes for chaotic dynamical systems, that the different toy models, and then find one universal kernel for prototypical dynamical systems. So what I have been after for really is exactly what you have in mind, which is universal kernel, but for prototypical dynamical system, chaotic dynamical systems. So prototypical universal kernels for function approximation, are now like Gaussian or inverse quadratic. But when you try them on chaotic dynamical systems, I mean, like prototypical ones like Bernoulli, Lorentz, Henon, and then later on like this 132 chaotic dynamical system, you could see that a simple Gaussian kernel or a simple inverse quadratic kernel will not work, will not do a good job dealing with all of them. So we want to attack this prototypical chaotic dynamical system at once. So that's the whole goal. In the same way, like that a universal kernel can attack a large class of functions and then can approximate them well. So the idea was the same, that I want to have universal kernel that allows to deal with a large class of chaotic dynamical systems. And simply, I mean, universal kernel, like as we know it, doesn't work. And that's why we had to do this tailor fitting. So I was doing it like bottom to top, where you you see, you're all right. I mean, you see the universal kernels are definitely here, but they were not enough. That was the issue. So one had to add extra terms, including, for example, the triangular kernel that we have here, and I mean that like was like a game changer in a way, because for the Bernoulli map, I mean it's homeomorphic to the 10th map, and the 10th map will give you the triangular kernel. So triangular kernel was quite important and then played a role. I mean, it's not clear that I don't know if it's like a universal kernel or not, but at least for dynamics, it allowed to do this. And another question, another actually possible answer to your question is that when we are learning dynamical systems, we are not only learning the function, but we are also trying to learn patterns. And so this is what I think these terms are doing, are learning pattern. For example, this term here with the exponential and sine, etc., is detecting locally periodic patterns. So this is what we call locally periodic kernel. And that's why I had to add that. So basically, in a way, instead of trying to learn the right-hand side, which is quite sensitive, I mean, if you look at the logistic map, you have the Rx, 1 minus x, and the regime is very different from 0. I mean, if you just change by 10 to the power minus 4, the regime will be totally different. So you cannot really focus on learning the parameters. What you want to do is learn the pattern. So and I think this is what this kernel is really doing, is that in a way you are doing a decomposition of different patterns that show up in this different dynamical system, and each of them is playing a role in pattern recognition for this chaotic dynamics. Yeah. So I would say, there are two answers, but I don't have any proof for them. But I guess intuitively, by just the way we are constructing them, it's mostly this. Yeah.
Okay.
I have a question.
Yeah.
So thank you for a great talk. Like most of the talks have been focused on kernel. I wanted to ask, kernels are really hard to compute. Just like k-nearest neighbors, they are very expensive and mostly work well for low-dimensional problems. So from practical point of view, how exactly do these kernels work well for high-dimensional problems like, parameters of a differential equation?
Yeah, they work quite well. So I'm not sure why you say that they don't work well for high dimensions, but they do work well for high dimensions. I see here I showed the example of climate modeling. So you see, I mean, it was like a high dimensional model. I mean, one of the things, the tricks that Rami Tmolik said that they do even in neural networks is to do PCA, so you have to do model reduction. So I guess it's not very different from other machine learning methods. But the kernel method do work for high dimensional models. I mean, it's not very high. I mean, I'm not talking about a case of infinite, like millions of variables, but even saw like yesterday for the case of PDEs. I mean, with in Humel's talk, they do well for PDEs as well. So so yeah, so they do suffer from curse of dimensionality, but they are not as different from neural networks, for example. So it's not, I mean, in a way, I would say that they suffer less from the curse of dimensionality than neural networks, because you have like less parameters to train than in the case of neural networks. So you have only, as I said, like in the case of learning this climate model, we use a parameter with 21, a kernel with 21 parameters. For the 132 chaotic dynamical systems, all we learned are 40 parameters. So you see, it's way more tractable than neural networks, for example.
Yeah, maybe let me be more specific. Like in terms of, I see that the way you derive your method is using Gaussian processes, and for you to make a prediction, you need to compute, the kernel distance from each sample realizations. Isn't that very expensive for testing purposes? Compared to neural nets, that once you train it, it's very cheap for test.
Yeah, but here it's also very cheap for test. I don't understand why you say it's not good for testing. But it's testing is quite similar too, because once you learn the kernel, all you have to do is to write down this expression, right? So this is your F now. You have your K, and then yeah.
Yeah, but this expression depends on the training data for each test realization.
No. I see. Yeah, actually, yeah. So okay, yeah, that's a good point. But actually, so actually, there is a way actually of doing it without training for testing. So you are talking about like when you have like an online. Are you talking about like an online version in a way where you have like a new points? What do you do? Is this what you are asking for?
Yeah, when you have a new point,
okay.
whether it's online or offline.
Yeah. That's very good questions. Yeah. So actually, there is a way. Kernel methods. I mean, there is a way of not doing actually all these computations. I mean, which is what we call like by working a Newton basis. But yeah, so it is possible. Yeah. So it's in the papers. If you look at the papers, but you can send me actually an email and I'll show you exactly what to do. But just look at basically Newton basis and the kernel methods, where you don't have to do the whole inversion and then the whole like so you don't have basically to rewrite the representative theorem for if you have like new points of testing. Yeah.
Okay, thank you.
Yeah, but that's a good question. So, but yeah, so it's there. It's in the paper. So there is a way actually of doing it. Yeah.
Yeah, I've worked on similar thing too, using something like hierarchical neighbor nearest neighbor worlds, kind of combining kernel method with nearest neighbors. Instead of having to search through the whole training data, you pick certain nearest neighbors that still retains the same information, but computation.
I don't know this, but yeah, please send me an email. I'd be interested in now what you are doing in the case of near neighbors, etc. Yeah.
Okay, thank you.
Yeah.
Okay, thank you very much. Nice discussions. And okay, let's thank the speaker again.
Yeah, thank you very much. Thank you.
Already time is delayed schedule.